Okay. Next, we'll take one more concept, that is virtual virtual ground or virtual short virtual ground or virtual short concept. So this concept we are using in almost all the applications of op-amp. So we'll see first what exactly it is. So say again, say we have one op-amp. This is negative, this is positive, this is pin number 2, pin number 3, and output is pin number 6. And we have input voltage, that is Vi. So Vi can be anything like 2 volts, 4 volts, 5 volts. Okay. So this input we are giving it to pin number 3. At the same time, we are grounding inverting terminal. Okay. So, I have two points here, or two terminals. Say this is V1 and this one is V2, and these two are basically not connected. Okay. So what happens is virtual ground means even though these V1 and V2 are not connected, okay, and whatever the voltage we can expect at V2, the same will appear at V1. Say Vi equal to 5 volts. Say Vi equal to 5 volts. So Vi equal to 5 volts means at V2 I can expect at V2 I can expect same 5 volts. Okay. So virtual ground means at V1 also I can expect the same 5 volts. This is the virtual ground concept or virtual short. See, basically these two are not connected even though we are considering the same voltage at the other terminal. So V1 equal to 5 volts. Say just check this diagram, looks a bit different. This is minus, this is plus, but this time I'm grounding the non-inverting terminal, and for inverting I'm providing some voltage, say Vi. Okay. So let's see how it works. So what happens is, say this is V1, this is V2. Since we have grounded non-inverting terminal, I can say V2 equal to 0 volt because it is being grounded here. And what our virtual ground concept tells, whatever the voltage we are expecting or we are getting at V2, the same voltage will appear at other terminal at V1 also. That is our virtual ground concept, V1 equal to V2. So at V1 also I am supposed to get the same 0 volt. So this is the virtual ground concept. So this we are using in almost all the applications of op amps. So first we'll start with the first application, that is op amp as inverting amplifier. Op amp as inverting amplifier. So first we'll draw the circuit diagram for this. So this is the diagram. So minus, this is plus. Inverting amplifier means straight away I need to ground the non-inverting terminal. Okay. So then so this is R1, this is Vi, this is RF, this is V naught. So in how it looks, so this is one op amp. Why inverting amplifier? Because we are given input only to the inverting terminal. At the same time, we are grounded the non-inverting terminal. And input, how we are giving? We are giving input voltage through R1, to the inverting amplifier. and we can see the feedback connectivity here. Means between inverting input and output we have one feedback resistance RF. Now what I can now what we'll do is, because of Vi I can expect some current, say it is I1. So because of Vi, I1 flows through R1, and this op amp has two basic parameters. Op amp has very high input resistance and very low output resistance. Since op amp has very high input resistance, it will not allow any I1 to enter into the op amp. So whatever the current that is flowing through R1 will straight away enter into the RF. Why? Because this op amp has very high input resistance, so it will not allow any current to enter into the op amp. Whatever the current that flows through R1 will enter straight away, that will flow through RF. So I can write, so this current I can make it as IF. IF means it flows through feedback resistance. So I can write I1 equal to IF, because high high input resistance of high input resistance of op amp. Say this terminal is V1 and this should be V2. Okay, so now we'll see, so can I write like V2 equal to 0? So V2 equal to 0 because non-inverting terminal is grounded, and we have one concept like virtual ground, V1 equal to V2, that is virtual ground concept. Means whatever the voltage that appears at V2, the same voltage will appear at V1 also. Means I can write V1 equal to 0. Okay, now I can call this as equation number 1. Okay, now I need to express equation 1 in terms of V and R. So our equation 1 is I1 equal to IF. I1 I can write like, it is the, say I1 means it is the current that flows through R1. So R1 is connected between V1 and Vi. So I can take the potential difference between V1 and Vi divided by R1. So V1 minus Vi by R1. Similarly, IF means it is the current that flows through RF. So RF is placed between two potentials, V0 and V1. So I can write like V0 minus V1 by RF. Okay. So this is say equation number 2. So this is say equation number 3. In equation number 3, what I can do is I can replace V1 by 0. From equation number 2 I can do this. From equation number 2 I can replace, from equation number 2 I can write, I can say substituting equation number 2 in equation number 3. Then what happens? Minus Vi by R1 equal to V0 by RF. So voltage gain means it is output voltage by input voltage. So V0 by Vi equal to minus RF by R1. This I am calling it as AF. It is the closed loop gain, V0 by Vi. So why we are getting minus sign here? Minus sign indicates that whatever the voltage or output voltage we are getting, it is inverted as well as amplified one.